Okay, welcome back, everyone. So this is the last talk of today. So our speaker is David Schaich from University of Liverpool, UK. David is going to talk about numerical methods in lattice supersymmetry. David, over to you.
Thanks for that introduction, and thanks also for inviting me to speak at this workshop. I'm sorry I haven't been able to participate to a greater degree, but I'm tied down here with teaching into June, and the 8-hour time difference means that the festivities are kicking off at 2 a.m. where I am, so that's been an obstruction. But I'm very glad to be able to tell you a bit today about my work in numerical analyses of supersymmetric field theories using lattice methods. This is something I've been involved with for a number of years now, with the most recent work being done in collaboration with a couple of today's other speakers, Anno Shinragav, as well as my PhD student, Angel Sherlatov, here in Liverpool, and Toby Wiseman at Imperial College London. And if I can get back to switching the slides again, the sort of central theme of what I'll be presenting today is that in order to make these numerical methods practical to investigate supersymmetric lattice systems, a key step is to formulate those systems in a way that is able to preserve at least a subset of these supersymmetries in the discrete spacetime of the lattice formulation. So that is the theme that we'll see following through after a brief motivation of why we're thinking about supersymmetric field theories through numerical lattice methods in the first place. We'll take a look at the details or some highlights of that formulation that preserves some of the supersymmetry and makes these numerical methods practical. And we will see through that process how we end up using a mix of some very standard and well-established numerical methods of lattice field theory, the same sort of thing that you would use or that one would use in lattice QCD, as well as some non-standard methods that are required by the different details of these supersymmetric field theories specifically. And it's very easy to fill the whole time just talking about that formulation and the setup of these systems, but I also want to just give some highlights of that as quick as I can to actually show off some of the physical results from these numerical analyses. So the starting point for that will be looking at somewhat simpler systems in 1+1 and 2+1 dimensions, where we analyze the thermodynamics that can be related to the behavior of black hole horizons through holographic gauge gravity dualities. And then if any time remains at that point, there are plenty of other things to talk about that also bring in some interesting numerical aspects, including the static potential of n=4 supersymmetric Yang-Mills theory in 3+1 dimensions, where we benefit from applying lattice perturbation theory and mixing that with the numerical calculations, as well as looks at the scaling dimensions of that superconformal system based on the renormalization group and MCRG, Monte Carlo renormalization group numerical methods. Finally, things, some supplements and ongoing work related to the sign problem evaluation of the Pfaffian in these theories, and the extension from pure supersymmetric Yang-Mills to supersymmetric QCD theories with matter fields, the analogs of quarks and squarks, their supersymmetric scalar partners. So before diving into that, I'll just say as a few logistic notes that if you want to look at any of the slides other than the ones I have on my screen, there is a link to them that should be in the chat window. Let me know if it did not come through, and also let me know if you have any questions or concerns as we go through at any point. I understand this is a broad audience and not necessarily the audience I usually speak to when talking about lattice supersymmetry. So I want to make sure that I at least uncover a little, and I prefer that to covering a lot. The main points have already been summarized here. So without further ado, let's talk about why we are worried about lattice supersymmetry in the first place, beginning with the fairly broad context of why do we care about supersymmetric field theories. And there are several directions that you can go based on supersymmetry. Maybe the most well-known one is its role in many proposed extensions of the standard models, this beyond standard model physics that is being searched for at many experiments around the world, including experiments at the Large Hadron Collider, so far without seeing any direct evidence for supersymmetry, but requiring very precise theoretical predictions in order to rule out the possibilities robustly. But at a more fundamental level, and the one that I'm more interested in and will focus on here, supersymmetry is really a tool, a symmetry that helps us simplify these very complicated, strongly interacting theoretical systems. So the applications of supersymmetry to deepen our understanding of quantum field theories has been really a major revolution over the past couple of decades, providing better analytic control over non-perturbative, strongly interacting phenomena like confinement and chiral symmetry breaking, conformality, and as well as what has now become one of the main pillars of theoretical physics, dualities, both electric-magnetic dualities relating different supersymmetric field theories, as well as this final point here, the holographic gauge-gravity duality I mentioned already, that relates these supersymmetric quantum field theories to stringy realizations of quantum gravity. And that is going to come up in some of the results we will get to. Now, where lattice field theory comes in is the promise of first principles predictions for these various supersymmetric quantum field theories without having to make any reliance on effective modeling or perturbative expansions. And to give you a reminder or possibly a brief introduction to how lattice quantum field theory proceeds, we can start from the perspective that we want to evaluate expectation values of some given operator based on the Feynman path integral formulation. So we carry out the integration over all configurations of fields phi defined at all points in space and time. We evaluate the operator for each of those field configurations, and then we weight the contribution to the path integral by the exponential of the action, where I have taken the liberty of performing a Wick rotation from Lorentzian to Euclidean space, so that this exponential factor comes in with a negative sign instead of a factor of I. And I am using my mouse to point at pieces in this equation as I talk about them, I realize, so let me know if that is not visible and I'll see what I can do about it. Now, the complication here is that in continuous space and time, there are infinitely many space-time locations for these fields to be defined. So this formally becomes an infinite dimensional integral over configurations of all of those fields at all of those points in space and time. And the lattice regularization of this infinite dimensional integral, to make it well-defined, it proceeds by formulating the theory in a finite discrete space-time of a certain number of points in space-time connected by links between nearest neighboring points. So that's illustrated in this diagram here, where the small spacing A between those nearest neighbor lattice sites effectively introduces an ultraviolet cutoff scale, the highest possible energy, and that is proportional to the inverse of that distance, 1 over A. So then removing the cutoff, getting from this regularized formulation back to the continuum quantum field theory of interest, requires extrapolating that lattice spacing to 0, so introducing more and more lattice sites packed closer and closer together so as to keep the overall size of the system L fixed, where we then recover the continuum quantum field theory in a similar sort of way as removing a hard momentum cutoff that you might see in an introductory quantum field theory course. Now, like other cutoff regularizations, this lattice regularization has the advantages of being gauge invariant, fully non-perturbative, not relying on any small parameters to expand in, and operating directly in however many dimensions are of interest for our calculation. It is also smarter than your average cutoff in the sense that the formulation on this regular discrete grid, this lattice, preserves a subset of the Lorentz symmetries or Poincare symmetries, Wick rotated to SO4 rotations group. The hypercubic rotation group that is preserved by, for instance, a hypercubic lattice suffices to guarantee that the full continuous translational and boost, rotational and boost symmetries in the continuum limit are automatically recovered in a way that does not happen with just a naive cutoff regularization. And this is actually a phenomenon that will reappear once we introduce supersymmetry into the game. First, though, another advantage of reformulating these quantum field theories in terms of a finite number of degrees of freedom is that we can numerically analyze them on finite computers, which is the connection to this workshop on numerical methods. So with the current state of high performance computing, it's fairly routine to evaluate systems with up to 1 billion degrees of freedom. So that path integral is formulated as a roughly billion dimensional integral. So we can think of, for instance, the Dirac operator governing the behavior of the fermions in this theory as a billion by billion matrix in this approach, where the bulk of the numerical computations will be repeatedly inverting these matrices depending on the values of the field configurations. So the numerical work that we have been done that will lead to the results coming up in a bit rely on computing centers mainly in the US and here in the UK. So it's worth acknowledging those contributions from the funding agencies supporting them. And just to say a few words about the algorithms that we use, this is very standard for the whole field of lattice field theory and even beyond. So I don't plan to go into any detail about this. Feel free to shout out if you have any questions or want to know more. But we design our algorithms to sample our field configurations with a probability that is proportional to their contributions to that path integral, specifically governed by this Gibbs distribution or Boltzmann factor that depends on our lattice action S as a function of all of those fields. The specific algorithm that we are using in all of this work is known as the rational hybrid Monte Carlo algorithm. And that I would say is the dominant algorithm throughout lattice QCD and lattice field theory more generally, accounting for well over 90% of investigations in that field. And once we have that approach to produce these samples of field configurations weighted by their probabilities, then the expectation values we are interested in are simply given by the average of the observables evaluated for some number of independent field configurations. This one of the many n's that will show up in this presentation, where n is simply constrained by the size of the computer and the length of time you are able to or want to run on it. And assuming that all of these n field configurations are decorrelated and statistically independent, the statistical uncertainties scale proportional to 1 over the square root of n in the usual way. Now that's all well and good, but there is an additional difficulty specifically related to supersymmetric field theories when we try to analyze them in discrete space-time, which is connected to the fact that may not be familiar to you, that supersymmetry is a space-time symmetry. It is an extension of that Poincare group of translations, rotations, and boosts that adds spinor generators, what I've called here Q and Q bar, that have an index I that range up to some number 1 to a different n. We will see n equal 4 super Yang-Mills in some detail a bit later. And specifically in the super Poincare algebra that results, we have relations like the anti-commutator of these Q and Q bar supersymmetries produce the generator of infinitesimal translations, the momentum, which simply does not exist when we have a discrete space-time without these infinitesimal translations present. So formulating a supersymmetric field theory in a discrete lattice space-time means that the super Poincare algebra is simply broken at the starting point, and that allows quantum effects in the calculation to produce any and all possible supersymmetry violating operators, many of which turn out to be relevant operators that then would have to be fine-tuned in order to recover supersymmetry in the continuum limit of interest. And I'll just mention that among the zoo of possible, of relevant supersymmetry violating operators, the most challenging ones are those related to the scalar fields that show up in either supersymmetric QCD with squarks or in extended supersymmetric field theories where the gauge multiplet includes scalars. Those scalars can pick up masses once supersymmetry is broken. They're 4 scalar 5 to the 4th quartic terms with various indices, can pick up different contributions that have to be accounted for, and similarly for their Yukawa couplings to the fermions, quarks and gluinos, which also pick up non-zero supersymmetry violating masses to be dealt with. So in principle, it's possible with infinite computing and infinite students to map out this fine-tuning problem in a high-dimensional parameter space, but that's not really practical. And the key insight in recent years that has enabled practical numerical analyses of supersymmetric lattice field theories is the realization that although some supersymmetry has to be broken by the discretization of space-time, it is possible in some situations to preserve a closed subalgebra of that super Poincare algebra, even at a non-zero lattice spacing, which, in analogy to the discrete hypercubic rotations recovering the full Poincare symmetries automatically at the continuum limit, then guarantee the correct supersymmetric continuum limit with little or even no fine-tuning. So there are 2 ways of going about this construction, either from so-called topological twisting or from dimensional deconstruction. I won't say anything about those topics. There's a nice review from over 10 years ago now. But the one message to take away from those constructions that I will just tell you up front is that in order for there to be enough supersymmetry for a subalgebra to be preserved, there have to be at least 2 to the power d supersymmetries in d dimensions. So if we look at 3 + 1 dimensions, this singles out one very special theory, the n = 4 supersymmetric Yang-Mills theory, that has 16 supercharges saturating this lower bound on the number of supersymmetries that are necessary. So let's look in some more detail at how that works, starting with a brief either review or introduction to the highlights of this n = 4 supersymmetric Yang-Mills theory. I'm sure this is something that is second nature to many of you in the audience, but some of you who might be coming from different backgrounds might not have encountered it before, but it's very widely studied in theoretical high energy physics, as it is arguably the simplest non-trivial quantum field theory that you can have in 4 dimensions. It has been used because of its simplicity. It has been a foundation, a cornerstone of a lot of work relating to scattering amplitudes, the development of electric magnetic dualities such as S-duality, as well as, of course, the CFT in Maldasena's original ADS-CFT conjecture that launched the field of holographic gauge-gravity duality 25 years ago. What it is an SUN gauge theory with 4 Majorana fermions that correspond to that N, which is not a coincidence, as well as 6 scalars, all of which appear in the same supersymmetric multiplet as the gauge field, and therefore are, like the gauge field, all massless and all transforming in the adjoint representation of this SUN gauge symmetry. And the reason this system with the gauge field, fermions, and scalars is so simple is because of all of the symmetries that it obeys. So these actually relate the coefficients of the kinetic, Yukawa, and phi to the 4th terms that you would naively write down from your simple power counting. And they include, in addition to these maximal 16 supersymmetries, so Q and Q bar ranging from 1 up to n equals 4, all of the indices on the supersymmetries and these fields refer to transformations under a global symmetry, what is known for historical reasons as an R symmetry, which is an SU of the script calligraphic n equals 4, which we can also replace by the SO6 that it is equivalent to, that SU4 is equivalent to for our purposes. Finally, the theory is conformal. It does not just have a conformal fixed point, it is exactly conformal at all values of the gauge coupling, which we will represent as this Tuft coupling lambda. So the n number of colors multiplied by the gauge coupling G squared. And because of all of these symmetries, the only parameters in the theory are this coupling and the number of colors, the non-calligraphic n. And in order to see how a subset of the supersymmetry algebra can be preserved on the lattice for this particular theory, I find it intuitive to take the approach of collecting its 16 supercharges, all of these Qs and Q bars, and arranging them in a 4x4 matrix, where as we go down each column, we are varying the spinor indices in that SO4 Euclidean group of, rotation group of Euclidean spacetime after that Wick rotation. Whereas if we go across each row, we are varying the index of the SU4 R symmetry. And given a 4x4 matrix, it is second nature to expand that in a basis of gamma matrices, what I've done here. So 4 times 4 being cast as a sum of 1 plus 4 plus 6 plus 4 plus 1 calligraphic Qs, which for later convenience, I will repackage in terms of 5 component objects. And I will be calling those scalar, vector, and antisymmetric tensor QAVs. So they add up to 1 plus 5 plus 10 components, reproducing the original 16. And as I was mentioning the role of the Lorentz index down each column and the R symmetry index across each row, we can appreciate this expansion in the basis of gamma matrices as producing coefficients or degrees of freedom, the calligraphic Qs that transform in representations of what is called a twisted rotation group, the diagonal subgroup of the direct product of the SO4 rotation group of Euclidean spacetime times an SO4 subgroup of the full SU4 or SO6 R symmetries. Now, in flat space, this way of writing things is just a change of variables. It has no effect on the physics of the system, but it gives us, instead of spinors, objects, the twisted supersymmetries, the calligraphic Q, that transform with integer twisted spin under this twisted rotation group. So that for lattice field theory experts in the audience, you can already be encouraged that we have avoided spinors in this way, knowing that spinors are much more complicated than integer spin objects in lattice field theory. In particular, if we consider the anti-commutator of this twisted scalar supersymmetry with itself, this turns out to be, well, it is just its square. This twisted scalar supersymmetry is a nilpotent operator. It squares to 0, which is a closed subalgebra of the full super Poincare group that can be preserved exactly on a discrete lattice spacetime. In effect, what has happened, or a way we can think about this qualitatively, is that we have constructed a linear combination of the original supersymmetries that, when squared, generates a linear combination of translations that circle back to the starting point that can then be identified with a single lattice site and really made infinitesimally small as demanded by the super Poincare algebra. So the other 15 supersymmetries are all going to be broken, as explained before, and it is just this one twisted scalar supersymmetry that is preserved and turns out to suffice to guarantee the restoration of all of the others in the continuum limit where the cutoff is removed. Of course, in order to work with the theory in terms of these twisted supersymmetries, we have to express all of its fields and interactions in consistent language. So recasting the 4 fermion fields in terms of this SO4 twisted rotation group, we again get the same integer spin representations, the 1 plus 5 plus 10 fermions that transform with either 0, 1, or 2 5-component indices with a fully anti-symmetric chi-AB. And for the bosonic fields, we have a 4-component gauge field and those 6 scalar fields. And what turns out to be best to do is to combine those 4 plus 6 degrees of freedom into a 5 plus 5 component complexified gauge field, so an A and A bar, that also run over the same 5-component index A. Now, the consequence of working with a complexified gauge field is that the SUN symmetry we are interested in is enhanced or promoted to a full UN gauge group. In the continuum where this formulation was first developed, that's irrelevant. The U1 factor that comes along can be decoupled at will. We will see that is not the case in non-perturbative lattice calculations, and actually that U1 factor that does not decouple is the source of some headaches that we've had to resolve to make our numerical methods really practical. But with this setup, and in terms of these reorganized degrees of freedom, we can check that the twisted scalar supersymmetry behaves as a supersymmetry should. If it acts on a bosonic field like this, the real part of the complexified gauge field, it gives a fermionic field, the psi fermion with consistent indices in all of these relations. And if we act again on that gauge field A, we get Q squared A equals Q phi, which then just vanishes, and similarly going across the other rows that account for all of the other degrees of freedom, where we introduce this bosonic auxiliary field D that will be replaced by its equations of motion, D bar, the gauge covariant derivative acting on the gauge field. And this helps preserve supersymmetry even off shell. Now, with this continuum construction, moving to lattice spacetime is not quite trivial, but it produces a system that looks nearly the same despite breaking 15 out of the 16 supersymmetries. We just have to replace those gauge covariant derivatives with finite difference operators, and the complexified gauge fields themselves get replaced by gauge links, which, as a non-standard method in this approach, unlike what is done in QCD, we keep the gauge links in the gauge group, or the GLNC algebra. I misspoke there. The gauge links remain in the algebra so that the supersymmetry relation between the gauge links and the fermion fields in the algebra continues to hold. And this is in contrast to QCD-like lattice analyses where the gauge links are placed in the group. And there's a nice now geometric interpretation for all of the fields that we have with all of their indices, that objects with no indices are identified with lattice sites. Those with a single index, like the gauge links, and what I'll call a link fermion psi, are identified with the links between the nearest neighbor lattice sites. And similarly with the chi-AB and the field strength tensor are identified with oriented plaquettes in the lattice. And the lattice action has exactly the same form shown here as the continuum action. Really all we need to worry about with this expression is that it remains supersymmetric. So the scalar, twisted scalar supersymmetry acting on this lattice action is identically zero. In the first set of terms in green, this follows from Q being a nilpotent operator and this being a Q exact portion of the action. Then there's also a Q closed piece, this last term with a 5-component epsilon tensor that vanishes identically through an exact Bianchi identity once that twisted scalar supersymmetry is applied and turns one or the other of those fermions into another set of covariant derivatives with an overall epsilon tensor. Now, you may have been wondering as I went through this, why we are working with 5-component objects in still a 4 or 3+1 dimensional spacetime. And I guess we've seen why in order to ensure that the supersymmetry algebra all works out as it should. Maybe the better question is how. And this is done by formulating the theory on what is called the A4 star lattice. So another non-standard aspect of numerical analyses of N equal 4 super Yang mills is that we cannot use the simple hypercubic lattice that is almost always used for QCD-like lattice studies. But instead, we are working on the 4-dimensional analog of the 2-dimensional triangular lattice that is pictured here. And we actually have to do this in order to preserve that final supersymmetry in the system that is crucial to restore all of the others in the continuum limit. So like the triangular lattice, the 5 basis vectors of the A4 star lattice symmetrically span 4-dimensional space. They are non-orthogonal and linearly dependent. And I guess the key aspect of this that has already been baked into the formulation presented earlier is the point group symmetry of the A4 star lattice structure, which is this large S5 group, even larger than the hypercubic group we talked about earlier. And if we have the time and inclination, we can go through the exercise of how the irreducible representations of this S5 point group exactly match on to the representations of that twisted SO4 rotation group in the continuum limit. So the 5 and 10 component objects transforming under the S5 map onto the vector and pseudoscalar components of the fermions under that twisted rotation group, and similarly for the 10-dimensional representation matching onto the antisymmetric tensor and pseudovector representations. And it is exactly the promotion of this point group symmetry to the twisted rotation group in the continuum limit that enhances the single scalar supersymmetry to restore the other 15. So that is the complete lattice formulation with some caveats that we'll get to. So let's just pause for a moment and perhaps regroup that we have developed this analytic lattice formulation of N equal 4 supersymmetric Yang-Mills theory in 3+1 dimensions, which we can also repeat in lower dimensions, 2+1 and 1+1, just by naive dimensional reduction or building up the twisting from from those lower dimensional cases to begin with. But the key aspect of this formulation is the high degree of symmetry that is preserved even in discrete lattice spacetime. There is the exact UN gauge invariance plus an exact twisted scalar supersymmetry plus the S5 point group symmetry that is enhanced to that twisted rotation group and ensures the recovery of all the other supersymmetries. And even based on this analytic formulation, you can show, the references are here and I won't go through the details. Thanks to these symmetries, the moduli space of the lattice theory is preserved to all orders in lattice perturbation theory. And the one loop beta function in lattice perturbation theory has been shown to vanish, which is certainly consistent with the exactly vanishing beta function of the continuum theory. And if you go through the exercise of constructing the long distance effective potential for the lattice theory, you can show that there is at most a single logarithmic tuning that may be required to recover the twisted rotation group from the S5 point group and then recover the full symmetries of the continuum theory. However, this workshop is focused on numerical methods, and there are still issues to resolve in order to make those numerical methods applicable to this theory. In particular, there are zero modes and flat directions that would cause the standard numerical methods of lattice field theory to break down. And these become especially challenging in the U1 sector and require some modifications to this very elegant and symmetric analytic construction. So one modification that is fairly trivial to think about and write down is lifting the zero modes in the SUN sector just by adding to the lattice action a scalar potential that is non-supersymmetric. You can see it only depends on the bosonic fields and no fermionic fields. So this explicitly breaks that last remaining supersymmetry, but it does so in a soft way. This is a soft supersymmetry breaking in the sense that all of the relevant supersymmetry violating operators that are now allowed to appear will appear with magnitudes proportional to this tunable coefficient mu squared that we just have to extrapolate to 0 when we take that continuum limit now. So as an illustration of this, we can measure violations of supersymmetric ward identities that take the form of that twisted scalar supersymmetry acting on some operator. And we can see, normalizing this ward identity violation by its magnitude, that as mu squared, the tunable parameter changes, the ward identity violations go very directly and linearly to 0 in the limit where we turn off this deformation we've introduced by hand to regulate numerical calculations. Now, this only addresses that SUN sector and not the U1 sector, which we can see by noting that the U1 sector corresponds to the complex phase that cancels out in the product of U times U bar. And we could consider just adding another supersymmetry violating potential based on some quantity that is sensitive to the U1 sector. The simplest such quantity is the determinant of the plaquette, the elementary face of the lattice structure. However, it turns out to be highly beneficial to go through things a bit more carefully and cleverly, and actually implementing some constraint on that plaquette determinant, in particular imposing that it should be close to 1, controlling fluctuations and 0 modes in the U1 sector. We can do that without breaking the supersymmetry by inserting this into the auxiliary field equations of motion. I will leave aside the details on that unless there are questions, but just contrast the effects that this has compared to the more naive approach I presented at the start. So the red points in this plot, which are again looking at violations of that same supersymmetric ward identity. the red points are what we would get with another naive supersymmetry breaking potential to regulate zero modes and flat directions in the U1 sector. This plot is on log-log axes, and these red points are, in fact, extrapolating to 0 in the continuum limit. So when L goes to infinity, and we go off to smaller and smaller values on this logarithmic scale. So we do have a valid formulation of the theory even with that deformation. But we can see that the red points are approaching 0 relatively slowly as the lattice volume increases, in contrast to the blue points that we get when implementing this constraint on the U1 sector supersymmetrically. And in particular, the slope of this line on the log-log axes is approximately 2, which means that we have effectively an order A improved lattice action by taking this approach. The violations of the twisted scalar supersymmetry are decreasing like 1 over the square of the lattice size, which makes it possible to get much better results from much numerically cheaper lattice calculations. So that is the full theory that we would analyze on the lattice using our rational hybrid Monte Carlo algorithm. You can see here it has a lot going on. So even though n equal 4 super Yang-Mills as a quantum field theory is particularly simple, its implementation for practical lattice calculations gets a bit complicated, in particular with over 100 internode data transfers for every application of that fermion matrix, the matrix vector product that forms the core of the conjugate gradient algorithm used to repeatedly invert this Dirac operator in the numerical RH and rational hybrid Monte Carlo calculation. So to avoid anyone who's interested in having to write this up themselves, there is parallel public code available to get you started with a user guide from a few years ago that is in the extended process of being updated to account for all of the additions that we have implemented over the past several years, including that supersymmetric deformation. See that as promised, the formulation section has taken up a significant chunk of the time. So not seeing any questions, I will move on to looking at some results, focusing on these lower dimensional systems, and in particular the thermodynamics of 16 supercharged maximally supersymmetric Yang-Mills in 1+1 and 2+1 dimensions, formulated on a torus in 2 dimensions. This is a space times time torus where a dimensionless temporal extent is simply related to the inverse dimensionful temperature divided by the square root of the dimension 2 Tooft coupling. Similarly, in 3 dimensions, we have 2 spatial directions, and the temporal extent is given by the dimension 1 Tooft coupling divided by the dimensionful temperature. In those lower dimensions, we have a larger number of scalar supersymmetries that are exactly preserved on the lattice, and we can identify a dimensionless temperature just as the inverse of this dimensionless temporal extent with the application of thermal boundary conditions, periodic for the bosonic fields and anti-periodic for the fermions. And the holographic dictionary applied to these maximally supersymmetric Yang-Mills theories relates their behavior at low temperatures and a large number of colors to the dynamics of black branes, black holes, and extended objects in the dual supergravity, the leading order term in the quantum gravity. So if we look at focusing here on the 2-dimensional theory with 16 supercharges, we can map the phase diagram as a function of the size and shape of the torus that the theory is formulated on. So that's what's shown in this plot, with the temporal extent shown on the vertical axis, so that low temperatures correspond to large R beta toward the top of the diagram. And as we change the spatial extent of the lattice on the horizontal axis, there are transitions predicted in two regimes. First, at high temperatures, all of the fermions pick up a large thermal mass from their antiperiodic boundary conditions. We have just a bosonic quantum mechanics theory where a first order transition is fairly easy to establish. And the opposite limit, the more interesting and more complicated one, where holography is reliable, there is the holographic prediction that if n is sufficiently large, there should be a first order transition from a homogeneous phase describing a black string, or a D1 brane, through a first order transition to a D0 phase of localized black holes. And by holography, this is mapped in the field theory to what I will call a spatial deconfinement transition, signaled by the Wilson line in that spatial direction that I've called PL through its analogy with the Polyakov loop. And throughout all of these phase diagrams, the system needs to be thermally deconfined in order for this holographic mapping to black hole spacetimes to be valid. So just to show you some of the numerical results that come out of our calculations in this simple two-dimensional system, the plot on the left is showing the trace of the Wilson line itself, our order parameter for this transition, which at high temperatures corresponding to a small temporal extent, the Wilson line trace is large and independent of the number of colors. And as we lower the temperature by increasing R beta on the horizontal axis here, there's a transition where the trace of the Wilson line becomes small and gets smaller as the number of colors increases towards the thermodynamic limit, where this transition becomes a true phase transition. The plot on the right is showing the corresponding susceptibilities of this trace that correspondingly increase. They scale with the size of the gauge group at precisely the same value of the temperature, where we can see the transition in the order parameter itself. And I should say here, what I've done is fixed the aspect ratio of the torus, the ratio of its spatial extent to its temporal extent. Here, that is fixed to a fairly large number, 4. So we have 16 by 4 lattices and 24 by 6 lattices, seeing no significant effects from changing the lattice spacing, increasing the number of points with everything else fixed. As a quick check of that extrapolation to an infinite lattice. And from this, we are able to identify the transition temperature for this relatively large aspect ratio. We can also look at these transitions by monitoring the behavior of the complex phases of the eigenvalues of those Wilson lines, interpreted. So the Wilson line is an n by n matrix. We diagonalize it, look at the complex phase of its eigenvalues, and depending on the confined or deconfined phase, spatially confined or spatially deconfined phase, the eigenvalue phase distribution has two distinct behaviors.
David,
so on the left plot,
David, you have 10
yes.
more minutes.
Yeah, I've been keeping an eye on the clock, so
Okay.
I will skip some of the higher dimensional stuff and leave some time for questions and discussions at the end before it gets too late for all of you. So the plots on here are showing the two different behaviors that we can have for the eigenvalues of the spatial Wilson line, depending on the phase that we are in. So in the left, we are looking at a small aspect ratio. So an 8 by 16 lattice at a lower temperature, T about 0.5 that on this plot would correspond to an R beta of 2, so well beyond the low temperature limit relevant for the large aspect ratio. And here, as we increase the size of the gauge group toward the thermodynamic limit, we can see that the distributions of these eigenvalues are becoming more and more localized around 0. So the going from green to red to black histograms produces a more and more sharply peaked distribution around that localized points that we interpret as or holographically that is interpreted as corresponding to the D0 phase of a black hole. And the opposite happens in the spatially deconfined phase. So this is looking at it on the right plot, an aspect ratio of 2, 24 by 12 lattice. So even though the temperature is even lower, the spatial length is larger. And in this regime, as we increase from blue to green to red histograms, going from gauge group SU6 or U6 up to gauge group U12, the histogram becomes more and more uniform around the angular distribution of these eigenvalue phases. So this is the resulting phase diagram that comes out of these numerical calculations that we can match onto the predictions at high and low temperatures and see that we reproduce the easier high temperature case quite well. And as we move to lower temperatures, we begin reproducing the leading order holographic prediction. I guess the challenge here is that the uncertainties on the lower temperature transition points become harder to control just due to the nature of those low temperature transitions. Increasing the number of colors should help improve that. But overall, the result is consistent with holography. And as Masanori might have told you a couple of days ago, the deviations from this leading order holographic prediction are very interesting to look at the full non-perturbative quantum gravity in a more strongly coupled and less well-controlled regime. So I will skip the discussion of the black hole energies that I'm sure Masanori told you about in 0+1 dimensions. I will wrap up by looking briefly at the 2+1 dimensional case, where we can carry out the same sort of exercise, at least in principle, though here the phase diagram becomes significantly more complicated now that we have both different spatial and temporal extents. There's a map of phase transitions as well as holographic relations shown by the dotted lines here. So don't need to say anything about this phase diagram because we won't be exploring it yet. We will just be focusing on the simplest phase, this D2 phase of holographic black 2 branes that I've circled in green, which corresponds to working on symmetric lattices of volume L³ and taking the continuum limit by extrapolating the number of lattice sites to infinity with a fixed temperature that then gives us a fixed spatial extent. So in this regime, we again have uniform distributions of eigenvalue, Wilson line eigenvalue phases. We can see going from 4 to 6 to 8 colors, these histograms again becoming more evenly distributed around the complex plane. And the key result here is the comparison of the energy predicted from the lattice calculation to the interpretation as the internal energy of this black 2 brane system. So at high temperatures, shown by the red line in this plot, the energy is known to scale as the cube of the dimensionless temperature, which we are approaching for T above around 0.4. And for lower temperatures, we deviate from that red curve and approach instead the low temperature holographic prediction at leading order proportional to a power of T to the 10^3, 3.3. And this is more recent work from just about 18 months ago and is still ongoing. with Angel Sherlatov here in Liverpool looking at different aspect ratios. But in this case, the big advance over what I was showing you before for 2 dimensions was the extrapolation to the continuum limit that we were able to do, shown on the right plot. So extrapolating to 1 over L squared going to 0, which we can see does not have much effect. Pretty much all of the extrapolations are consistent with a flat line, consistent with a constant within their uncertainties. And the uncertainties themselves are fairly large, as we can see in both plots. So given the time, I will skip over the discussion of the static potential in 4-dimensional n=4 super Yang-Mills theory and the role of tree-level perturbative improvements to produce these nice pictures of a Coulombic static potential that gives us predictions for that Coulomb coefficient that match on to perturbation theory. Similarly, skip the brief discussion of conformal scaling dimensions in this superconformal n=4 theory that also are consistent with perturbation theory throughout the range of couplings we're able to access. I will just mention that this range of couplings is, at least at the present, limited by the onset of sign problems. So the possibility that the Pfaffian of our fermion operator picks up a phase that deviates significantly from being real and positive, depending on the lattice volume and the coupling. We actually don't see significant effects with the lattice volume, which is a contrast to, say, QCD at finite chemical potential, where the volume is the sign problem is very sensitive to the volume. What we do see, however, is a big effect on the sign problem setting in as that 't Hooft coupling increases, and there's work ongoing to try to improve that, as well as to try to formulate supersymmetric QCD using the same twisted formulation that guarantees the recovery of the continuum limit with much less fine tuning. This is what Angel Sherlatov is focusing on for his PhD project. So obviously a lot going on. I hope that it was interesting or entertaining to hear a bit about numerical analyses of lattice supersymmetries and the numerical methods that we have to apply for these analyses. So the key, as I said, was to preserve at least a subset of the supersymmetries in the discrete space-time of the lattice. That is really the only way that these particular investigations of lattice field theories are numerically practical. And using that formulation, we've been able to obtain results for thermodynamics in 1+1 and 2+1 dimensions that are consistent with holography. And there's a lot of work ongoing to explore the superconformal 3+1 dimensional n=4 supersymmetric Yang-Mills theory that brings us into ongoing work with the sign problem and explorations of supersymmetric QCD based on the lower dimensional formulations. So that is all I will say. Thanks for your attention, and I'm happy to take any further questions that you may have on any of these topics.
Thanks, David, for a nice talk. Time for questions. So maybe I can ask a question. So David, on one of the previous slides, you showed lambda lat, 't Hooft coupling on the lattice.
So that shows up in the horizontal axis of plots like this, or this one for the static potential.
Yeah, to make connections with the, what people have computed from string theory, do we know the conversion between lambda lat and the other lambda?
So that is a good question. And the answer is that we know some aspects of that conversion, but there is the possibility for a non-trivial renormalization of the lattice coupling. So that is a bit of a long story in another project that is happening slowly with Angel Charlatov and Georg Bergner. So the issue here is that if we had a superconformal field theory, there would be no running of the coupling. That's what a vanishing beta function means for a conformal theory. So we would have then just a direct conversion from the lattice coupling to the continuum one, just dependent on the lattice structure. However, when we impose that ultraviolet cutoff given by the lattice spacing and also have an infrared cutoff given by the finite extent of the lattice that goes into our finite computers, both of those are explicitly breaking conformality and can in principle lead to a controlled renormalization of that Tuft coupling. So the lambda lat is what goes into the lattice action at this cutoff scale that defines the lattice spacing, or defined by the lattice spacing. And by doing, well, that it is possible that that coupling can flow to some extent before the quasi-conformal dynamics kicks in, away from both those infrared and UV and IR regimes. And in order to quantify that, you would like to carry out some analysis of the running of that coupling, where the Wilson flow or gradient flow is the standard numerical method to do that in modern times in lattice field theory. What I've done in this plot is actually just fit the red diamonds, so the U4 gauge group with an 8 cubed by 24 lattice, I fit those to the leading order continuum perturbation theory and use the coefficient of that fit as the conversion factor between lattice coupling and continuum coupling. So the dashed line on this plot is just imposing a constant renormalization factor between those continuum and lattice couplings, and it is work in progress to predict the running of the lattice coupling due to the breaking of conformality by lattice artifacts. That I think is yet another interesting numerical topic that obviously did not have time to fit into today's presentation.
Right. Okay. Any other questions? No questions from here. How about audience on Zoom? Any questions from Zoom? So seems like no questions from Zoom. So let's thank the speaker again.
Thanks for having me.